Welcome to class, ladies and gentlemen. Happy Tuesday, if that's when you're watching this video. Mr. Eicher here to talk about graphing rational functions. So, on this page in your notes, it says determine the equations of any vertical asymptotes, the coordinates of any points of discontinuity, and the equations of any horizontal asymptotes. So we got vertical asymptotes that look like this, little vertical dashed line that the function approaches, maybe kind of like that. Points of discontinuity, which is the lines going along, minding its own business, and then there's a big hole in the line, and then it just continues. That's a point of discontinuity. It is not continuous line, it is discontinuous. And then a horizontal asymptote, that would be a horizontal line dotted that we saw when we had exponential functions in the last chapter. So let's review. How do we get, or how do we know when one is one versus the other? So a vertical asymptote, anytime you have a factor, a binomial I should say, in the denominator that cannot divide out with a binomial in the numerator, like this x minus 2, you take that denominator and set it equal to 0, x minus 2 equals 0, and that tells you that x cannot be 2. I hope that makes sense. If you had this equation, put a 2 in for x minus 2, it would be 1 over 0. That is undefined. 1 divided by 0 is not defined. It makes no sense. You can't have 1 of something that never existed. For points of discontinuity would be, what if we had a factor of x minus 2 in the numerator? So this function right here has factors that would divide out. So if you plugged x equals 2 in, it's not as big of a problem because the x minus 2's are going to divide out. But for the original function, it still is a problem. You can't plug 2 in because it would be undefined when you plug 2 in for x. So that's vertical asymptotes and points of discontinuity, looking particularly at the denominator. For horizontal asymptotes, we talked how to determine those in a previous lesson, so let's turn back one page in our notes. So you might remember with horizontal asymptotes, we have to look at the degree of the numerator and the degree of the denominator. So I kind of like to circle them like that. So we have a degree 2 and we have a degree 2. If the degrees are identical, then the horizontal asymptote would be the coefficients, 1 over 3. Why is that? Well, if you tried plugging in a very large number in for x, like 1,000, and 1,000. That 1,000 would go, 1,000 squared is going to be a very large number, one with 6 zeros. Now you can add 7,000 to that and then plus 12, but these really don't contribute as much as that first term. And in the denominator, the 7x isn't going to contribute as much as squaring 1,000. So really you can think of this as a simplified version. You get x squared over 3x squared. The x squareds divide out and you're left with 1/3. So your horizontal asymptote, if you graph that, you would have a horizontal line at 1/3. So that's one case. If the degrees are the same, then you take the coefficients. Another case is if the degree in the denominator is larger than the degree in the numerator. In that case, imagine putting 1,000 in here, 1,000 squared. That's going to be one with a bunch of zeros. Which that's a pretty big number, but notice what happens here. You do 3 times 1,000 to the 5th. Oh boy, that's a lot. That would be this many zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I think you'd have 15 zeros. So yeah, sure, that's a big number, but this is huge compared to that. So if your denominator has more weight, or if your denominator is going to be huge number, big number, and your numerator is going to be not as big number, small. A small number divided by a big number is approaching 0. So the other case, like this one, if the degree is larger in the denominator compared to the numerator, then your horizontal asymptote is at y equals 0. So when you graph, you would have a horizontal asymptote at the axis, y equals 0. The other situation that we can come across is, really, there's only one other case, right? This first case here, they're equal degree. This case here, the denominator is bigger. And now this case, the numerator is bigger. So what happens when you have that case? Well, we'll be talking more about that later in this lesson. But just to give you a preview, you won't have a horizontal asymptote. It actually becomes an oblique asymptote. An oblique asymptote is a diagonal asymptote that the function follows, maybe kind of like that. So we'll be talking more about that, but it's important that you can identify what's the equation of the horizontal asymptote. So let's go back to that first page of today's lesson and check out those questions. What I would like you to do is answer questions number 1 and number 2. You'll need to factor in both of the questions, factor the trinomials, and then determine what are the equations of the vertical asymptotes, the points of discontinuity, and the horizontal asymptotes. So pause this video and answer number 1 and 2. Factoring the first, we get identical factors of x plus 2. So since those factors will divide out, that will tell us the location of a point of discontinuity. And that point would be setting the denominator equal to 0. So you get x equals -2. At that location, there's going to be a hole in the graph. This other factor here that is in the denominator, we set equal to 0, and that tells us the location of the vertical asymptote. So you get 2x minus 3 equals 0, so there's a vertical asymptote at 3/2. And if you need extra time to factor and finish number 2, pause this video. For number 2, we factored. One helpful tip about this chapter is if you can't figure out how to factor something, probably there will be similar factors in the numerator and denominator. So like we get these factors here. So if you can't figure out how to factor that numerator, but you're able to figure out the denominator, then 3x minus 1 would be a good guess for a factor. So this will give us a point of discontinuity at 3x minus 1 equals 0, so that would be x equals 1/3. Whereas this one, the one in the denominator, gives us a vertical asymptote, and that would be at x equals -1. I need to go back, and now I will identify the horizontal asymptotes. Notice here the degrees are the same degree. So that means as you put in large values of x, the numerator and denominator grow at the same rate. So the horizontal asymptote would just be the coefficients, 3 divided by 3. So that would give us y equals 1. So when we sketch this, we would have a horizontal asymptote at y equals 1, and a vertical asymptote at x equals -1, and a hole in the graph somewhere at positive x equals 1/3. For the other question on number 1, the horizontal asymptote, we look at the degree, and the degree is bigger in the denominator. So if the denominator is getting bigger faster, then this quantity is going to be approaching 0. Horizontal asymptote at y equals 0. If you don't believe me, you could just put a large number in there, say 100. 100 plus 2 over 2 times 100 squared. 100 squared would be that, plus 100 minus 6. If we evaluate this, this would be 102 divided by 20,000. So about 100 divided by 20,000. That's going to be about 1 over 200. That's a very small decimal. What is that, 0.05, something like that? So that's getting closer and closer to 0. Alright, so let's look at a graphical approach identifying these types of characteristics of rational functions. Let's walk through number 3 together, and then I will have you attempt the second two next to that. So using the following graphs, identify all the asymptotes, points of discontinuity. So first, VA, vertical asymptote, we can tell that's right here. That's at x equals 1. Make sure you put x or y equals. This is a vertical line, so it's x equals. Notice the directions here say horizontal or oblique. You can't have both. And this diagonal line is an oblique line. It looks like it starts at 1, and it has a slope of up 2 to the right 1, up 2 to the right 1. So that would be a slope of 2 with a y-intercept at 1. So our equation for our oblique asymptote would be y equals 2 is the slope and 1 is the y-intercept. And then lastly, we have a point of discontinuity right here, and it looks like the coordinates are 2, 6. 2, 6. So that's using graphs to identify the characteristics, the asymptotes, and the points of discontinuity. I'd like you can work with your neighbor to answer the next two, identify the equations, and when you come back, the answers will be provided on the screen. So pause this video. Welcome back. We have vertical asymptotes at -3 and at +1. We have a horizontal asymptote at y equals 2. And in blue, we have the point of discontinuity as -4, 7. And then the third graph, we have a vertical asymptote at 2, we have a horizontal asymptote at 3, and we have a point of discontinuity at -3, what looks like 2.5, -3, 2.5. And both of these had horizontal, not oblique. It's one or the other. So let's summarize these topics below. So vertical asymptotes, you look at the denominator of some rational function, and if the denominator can't divide out with a factor in the numerator, I'll just spell it out, numerator, then it's a vertical asymptote. You set it equal to 0 and solve. A point of discontinuity, divide this up. A point of discontinuity would be a situation like this, where you have factors that divide out. Factors divide out. You set that factor equal to 0 and solve, and that tells you the location of a point of discontinuity. Once you find the x-coordinate, you would plug in the x-coordinate into the function to find the y-coordinate of the point of discontinuity, and we'll do that a little bit later. Next, with a horizontal asymptote, there's a couple different cases. Number one, if the degree is equal, let's say you have something like this, 4x cubed minus 7. You look at the degree of the top and the bottom, and if the degree is equal, comma, then you have a y equals 3/4 in this case. You use the leading coefficients of those terms that are the highest degree terms. if the degree in the bottom, degree in the bottom is bigger, then your horizontal asymptote is y equals 0. The denominator grows faster, grows to be a bigger number than the numerator, so a small numerator divided by a big denominator is 0. And then lastly, oblique asymptotes occur when you have the degree in the numerator is bigger than the degree in the denominator. In the method or the approach that we use to figure out our oblique asymptotes is synthetic division, our old friend, synthetic division. And we'll review that very soon. Alright, so now, instead of being given graphs, on this next question we'll be given the equation and asked to determine all these characteristics and try to figure out what the graph might look like. Alright, let's begin with number 4a. Let's begin by factoring. Well, over here on the right, I guess we can quickly identify the degree of the top. It's degree 2, that's the highest exponent. The degree of the bottom is degree 2, that's its highest exponent. So that tells us that the horizontal asymptote, since these degrees are equal, we would look at the leading coefficients. This leading coefficient is a 1, this leading coefficient is a 1, so our horizontal asymptote is y equals 1. To find the other two we have to factor, so we can factor this as in an x minus 4 and an x plus 3. And then the denominator we can factor to be x plus 3 and an x minus 1. So the denominator is what you look at to determine the vertical asymptotes and the points of discontinuity. This x plus 3 factor and this x plus 3 factor, they divide out. So any factors that divide out like that tell us the location of the points of discontinuity. So setting this x plus 3 equal to 0, we would get x equals negative 3 is a point of discontinuity. Whereas this one does not divide out with anything. So setting that equal to 0, we would get x equals 1 is a vertical asymptote. So I think that's all that we're asked to find. We have our horizontal asymptote, we have our point of discontinuity, and we have our vertical asymptote. When we get to the next page, we'll put it all together in graph, but let's continue practicing identifying these different characteristics. On letter B, I'd like to see if you can state the degree of the top and bottom, factor the denominator, it's a trinomial, so factor that, and then see if you can list the VA, POD, and HA. So pause this video, see if you and your neighbor can figure that out. So to factor, we have x minus 1 in the numerator still. Factoring the denominator, 2x times x would give us this 2x squared. I need factors of 3. To be careful where I put these, we'll put the 3 here and the 1 here. We have to be careful because this plus this product needs to give me that middle term. And I have a 3x and a 2x, that should get me to a 1x. As long as I get my signs right, I need that to be a positive x, so that should do it. The degree in the top and bottom, the top is a degree 1, that's that 1 right there, and the bottom's a degree 2. So since the bottom is a higher degree, our horizontal asymptote would be at y equals 0. The bottom grows faster. So the function's going to approach 0 as it goes to infinity. Again, you look at the denominator for your possible VAs and PODs. This one set equal to 0 would be x equals negative 3 over 2, and this one set equal to 0 would be x equals 1. That's where the function is undefined. Which one is which? Well, this one here does not divide out with anything in the numerator, so this would be a vertical asymptote. Whereas this one, the x minus 1, divides the numerator and the denominator, both have an x minus 1. So that tells us that the x equals 1. What type of break in the graph is it? It's a point of discontinuity. So we have our horizontal asymptote is 0, our point of discontinuity is 1, and our vertical asymptote is x equals negative 3 over 2. Before we move on, I'd like to talk about how to find the coordinates of the point of discontinuity. We found the x-coordinate. How do we find the y-coordinate? Well, you take the simplified version, 1 over 2x plus 3, and you plug that 1 into the x, so that would be 1 over 2 times 1 plus 3. So the y-coordinate for the point of discontinuity is 1/5. So really our coordinates for the point of discontinuity would be 1, 1/5. That'll be helpful later when we're graphing them. Let's look at the next one. This would be a perfect example for a try this problem. I'm not there, but you can see if you could manage doing a try this problem if you're really interested. But otherwise, pause this video, see if you can complete this correctly. So the denominator we look at, that gives us an x equals negative 1, the function's undefined, and at x equals 4, the function's undefined. Which one is which? What type of break in the graph is it? Well, the x minus 4's divide out, so anytime they divide out, you get a point of discontinuity. Whereas the x plus 1, there's no x plus 1 in the top, so that would be a vertical asymptote. The degree of the top, we have an x, and an x, so that would be degree 3. And in the denominator, we have an x and an x, that would be a degree 2. So we do not have no horizontal asymptote. So we have a vertical asymptote here. The y-coordinate of our point of discontinuity, we would take the simplified version, so that would be x minus 1 times x plus 2, I'll put in the x's in a second, over x plus 1. I put in my 4 that I got right here into the simplified version of the function. So that would be 3 times 6 over 5. So our point of discontinuity coordinates would be 4, 18/5. You often get a fraction when you plug in the value to find the y-coordinate of the point of discontinuity. So our point of discontinuity would be this, 4, 18/5. Now up here we said that there's no horizontal asymptote. I'd like to look at on the next page, what do we do? Do we have some kind of asymptote? And we do. This situation, when the top's bigger, that would give us an oblique asymptote, one of those dashed diagonal line asymptotes. But let's wait for the next page to dive in to figure out how do we solve for one like that. So let's go to the next question. So about oblique asymptotes. As the directions say, find the oblique asymptote for the following using synthetic division. We can only use synthetic division when we're dividing by a binomial, a degree 1 binomial. So notice first the numerator has a bigger degree than the denominator, so it's not any horizontal but an oblique asymptote. So to calculate an oblique asymptote, we set up our synthetic division. The denominator, the number is the opposite, so not positive 1 but negative 1. And we're going to put a 3, an 8, and a negative 3, our coefficients at the top. We're going to bring the 3 down, multiply by negative 1, add, multiply, and add. This is our remainder. And remember what these values tell us. That would be our depressed polynomial is the name of it. We started as an x squared, we divided out an x, so this tells us 3x plus 5 minus 8 over what we're dividing by. So to be able to determine the equation of the oblique asymptote, the equation of the oblique asymptote is this value, this equation right here. So y equals 3x plus 5. Why don't we care about the remainder? Well, as x goes to infinity, say you put like 1,000 in here, this definitely changes. That would be 3,000 plus 5. But this quantity right here, that quantity is approaching 0, so it's irrelevant basically. 8 divided by 1,001 isn't going to contribute very much to our 3,005 over here. So you ignore the remainder, and you just use these coefficients to determine the equation of your oblique asymptote. So oblique asymptote OA would be y equals 3x plus 5. There we go. Let's look at the next one. This example is a great question for a try this problem, and what I would ask is see if you can use synthetic division correctly to determine what the equation of the oblique asymptote is. So if you'd like some time, you can pause this video and you can see if you can do that question. Here's what I got when I did synthetic division. Feel free to check my work. But the numbers we're interested in are these two. Our equation of our oblique asymptote would be 2x minus 1. And that's it. So if we were asked to graph, we would start at negative 1 and we go up to over 1, and then, whoops, that would be a dashed line for our oblique asymptote. All right, let's move over to C. You'll notice that the numerator is a x cubed minus 1. And I have a little note here, difference of 2 cubes. So how will we approach this? Well, let's try to factor the top and the bottom. You may or may not remember the formula or the pattern. If you had a cubed minus b cubed, that factors to be what? Kind of ran out of space here. It would factor to be a minus b, a squared plus ab plus b squared. So we can factor this numerator to be x minus 1, x squared plus 1 times x plus 1 times 1. And the denominator we can factor to be x minus 3 times x minus 1. Notice we have a candidate for a point of discontinuity right here. So we would have a point of discontinuity at x equals 1, since we can divide out that x minus 1 factor. However, once we've divided it out, we have x squared plus x plus 1 divided by x minus 3. The degree in the top is 2, the degree in the denominator is a 1, so that means the top is a bigger degree, so we use synthetic division. We can set that up. That would be a positive 3 out here. 1, 1, 1, that's nice. Bring the 1 down, multiply, add those, multiply, add those. This is our remainder. So it looks like our equation of our oblique asymptote is the equation y equals 1m plus 4. Don't really need the 1 there, but I'll write it there so you can see where I got that slope, which was from this number here. We also have a vertical asymptote at x equals 3. That was from this factor that didn't divide out in the denominator. So I hope that was good practice for determining these. Now I'd like to practice some graphing situations. So let's move on. Now we're bringing it all together. We've learned a lot of skills in this lesson. Let's see if we could bring it all together and create a graph of a rational function. Let's begin by using synthetic division. Notice that we have a degree here which is a degree 2, and this is a degree 1. So we can set up our synthetic division with the 4 on the outside, 2, negative 11, and positive 16. Bring the 2 down, multiply, add, multiply, add. So we get an oblique asymptote at y equals the line, y equals 2x minus 3. Since we just got that, let's graph that. We'll graph negative 3 on the y-axis. We'll go up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, etc., etc., etc. There we go. So this is our vertical, sorry, definitely not vertical. That's our oblique asymptote. We can tell by the denominator here, it doesn't have any factors in the numerator that'll divide out. So we would get a vertical asymptote at x equals 4, x equals 4. So we can graph that vertical asymptote at x equals 4. So a good way to think of this, we kind of have 4 regions. We have a region here, a region here, a region here, and a region here. So we're going to have branches. Just 2 of the 4 regions are going to have branches. Otherwise it wouldn't be a function. So let's see what regions we have points in. You're provided, just to make it nice for you, a table of values. So let's graph those values. You have 0, negative 4 is right here. 3, negative 1 is right here. And then 6, 11 is right here. So that should give you an idea of what 2 of the 4 regions have points in them. The rational function is going to be close to the asymptote, go through those points, and then follow the other asymptote down. And then it's going to follow this vertical asymptote and come like that. So that is our rational function. Very colorful too if you're using different colors. Alright, let's look at the next example. So, notice that the degree in the numerator is bigger than the degree in the denominator, so that's a synthetic division candidate for an oblique asymptote. We start with a positive 1 on the outside, negative 1, a 5, and a negative 2. Do synthetic division, drop that down, and multiply, 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 multiply. Add. That's my remainder. So we have an oblique asymptote at y equals negative 1x plus 4. Let's graph that. Our y-intercept's at 4. That's our starting point. And our slope is negative 1, so it's a downhill slope going downhill. There we go. Continue it a little bit in the other direction. Perfect. So that's my dashed oblique asymptote right there. And then we have a vertical asymptote, set the denominator equal to 0. that would be x equals 1 is our vertical asymptote. So we can graph that. X equals 1 is a vertical line. And again, we have 4 regions. We have one here, one here, one here, and one in here. So the table of values on the bottom left gives you an idea of where our function is. So graphing the points in the table, we have -2, 5.3. That looks like it's right about here. We have 0, 2 is right there. 2, 4, and 6, -1.6. Maybe right there. So it looks like our function goes like this. We follow this asymptote, hit the point, and then go down like that. And then start up here, follow the asymptote down, get close to the other asymptote, and go like that. So I hope you could see how helpful those points are. These points here, 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 and here, to give you a little more sense of what the graph looks like. So that's 2 graphs. I'd like to see if you can work with your neighbor to figure out the next type of graph. So on number 7, similar question, however, notice the denominator's been factored. The denominator is a bigger degree, the degree of the denominator, degree of the numerator. Degree of the numerator is degree 1, degree of the denominator is degree 2. I'd like to see if you can remember and identify. Would that be an oblique or horizontal asymptote? I hope you said horizontal asymptote. When the degree in the numerator is bigger than the denominator, that's when we use synthetic division. In this case, it's flipped. So we get a horizontal asymptote. That would be at y equals 0. The denominator's growing bigger faster, so if the denominator is bigger, then it's going to approach 0 as x approaches infinity. So what kind of graph do we have here? Well, first let's look at the denominator. Neither one of these factors will divide with the 2x. So that means we have 2 vertical asymptotes. We have one at x equals -2, and we have one at x equals +5. So let's graph that. We have x equals -2, that would be this line as a vertical asymptote, and x equals +5 is this line. And we said earlier that we have a horizontal asymptote at y equals 0. Now in this case, we have 1, 2, 3, 4, 5, 6 regions. So we're going to fill up half of those regions. That would be my guess. Can't really fill up 4 out of the 6 because it wouldn't be a function. So we need 3 branches, 3 parts of our graph. Points of discontinuity, there are no factors that divide out. No factors divide out. Therefore is a little triangle, 3 dots. Therefore, there are no points of discontinuity. So I guess just at this point, we'll use our points in the table. We have a -3, -0.7, somewhere like that. We have a -1.5, comma, -1.5, comma, 0.9. It's kind of up there-ish. We have 3, comma, -0.6, 3, -0.6, and we have 6, comma, 1.5. Oh. Uh-oh. I didn't realize that we were counting by 2's on that scale. Make sure that I did these right. Counting by 2's on every scale. Okay, so we have -3. Okay, that was right. And then, okay, so that one looked good, my first point. Close enough. Negative 1.5 would be here up to, okay, so maybe we're like right about there. Negative 1.5. Oh, yeah, I'm kind of struggling with these scales being different. Negative 1 is here, 0.5, and then up 0.9. There we go. Right there. And then 3, 1, 2, 3, and then down negative 0.6. That's not going to be very far. And then 6. Okay, that's labeled as 6. And then 1.5. 1, that's a 2, 0.5 is right about there. Okay, thanks for your patience with that. So what would our graph look like? Our graph would look like this branch. Go all the way down. At this location right here, the numerator equals 0. So I'm guessing it looks like this. And then the last region is like this. So the way that I figured out this point is the numerator is 2x over blah blah blah, whatever the blah 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 is. When the numerator equals 0, that gives you an x-intercept, which was that point right there. So actually my conjecture of how many regions we would be in wasn't good, because we have a region here, we have this region, still a function, and then this region. So it actually was possible to be in 4 out of the 6 regions. Interesting. Alright, let's look at our last graphing example. Number 8. See if you can identify the x-coordinate of the vertical asymptote, the x-coordinate of the point of discontinuity, and then see if you can graph the vertical asymptote and figure out the horizontal asymptote. So if you'd like to pause this video, see if you could figure out a couple of those components. For the vertical and asymptote and point of discontinuity, we look in the denominator. When is the denominator undefined? Well, that would give us, this one would give us x equals 2. The denominator would be undefined, or the fraction would be undefined. And then x equals negative 2. But which one's which? Well, this x plus 2 and this x plus 2 would divide out. Anytime you have factors that divide out, you get a point of discontinuity. So you have x equals negative 2 as the point of discontinuity. If you hear that rustling in the background, my puppy was playing with her toy. And then our vertical asymptote would be the factors that don't divide out. We would get an x equals 2. It would be nice to know what's the coordinate of the point of discontinuity. Well, with the simplified fraction dividing out the x plus 2's, we would get a 3, x plus 1, and a x minus 2. We're going to plug in the negative 2 into that, so 3, negative 2 plus 1 over negative 2 minus 2. That would be, let's see, negative 3 over negative 4. So our coordinates of our point of discontinuity would be negative 2 for the x and 3/4 for the y coordinate. Okay, we're almost there, almost ready to graph. All we need is the horizontal or vertical asymptote. Well, in this case, the degree in the numerator is 2 because you have 2 x's. The degree in the denominator is 2 because you have 2 x's. So you'd have like something like a 3x squared in the numerator, and then you'd have an x squared in the denominator. Now you'd have some other stuff after that, but that shaking was my puppy letting me know she wants to be let out of the room. As I was saying, to determine the horizontal asymptote, since these degrees are the same, we would look at the leading coefficients, which is a 3 over 1. So our horizontal asymptote would be at y equals 3. So putting this all together, we would have an x equals 2 vertical asymptote, a y equals 3, horizontal asymptote, a point at negative 2 comma 3/4, there's a hole in the graph. Okay, and let's graph some of the other points. We have 0 comma negative 1.5. I think that's right about here. And then we have 4 comma 7.5. That would be right about here. And that actually would be enough to help us graph. We would have a graph that looks like this. We have a hole in the graph right there. And then this one would be like that. Actually does kind of stretch out. I want to kind of fix that because it doesn't look very nice. There, that's a little better. Where the hole in the graph is here. There we go. So, I hope this was a helpful video for you. A lot of skills determining characteristics of rational functions. Thank you for watching, and I will see you soon.